Hello everyone, welcome back to the course on Introduction to Multi-Agent Systems. In the previous lecture, we talked about some algebraic graph theoretical properties associated with the adjacency matrix. In today's lecture, we will try to look at some graph theoretical properties that we can associate with the adjacency matrix. So, let us get started. So, suppose we start with some weighted digraph G which has at least 2 nodes and which has a weighted adjacency matrix A. Then the following statements are equivalent. First is the matrix A is irreducible. So, the definition of irreducible is equal to this, which we have looked at in the past as well. The second property is that there does not exist a permutation matrix P such that PAP transpose is block triangular. Notice that does not exist. Okay. The third property is that G, the graph G is strongly connected if the adjacency is irreducible. And the fourth property is, now we have the set of nodes 1 to n and we can partition the nodes into 2 sets I and j. Then for all the partitions I to j, there will exist some I belonging to the node set capital I and some j belonging to the node set capital J, such that there exists a directed edge from I to j, meaning in whichever way we partition the nodes such that this is capital I and capital J, we can always find an edge from I to j. Okay. Let us try to look at the proof of this result, which is very straightforward. Okay. Let us start with the simple case of just a moment. A to C. Let me quickly remind you what was A and what was C. So, A was that A is irreducible and C says G is strongly connected. Let us write it here. The adjacency matrix A is irreducible, implies the graph G is strongly connected. SC simply implies strongly connected. Okay. Let us try to prove this. Now, A being irreducible means summation of A to the power k, where k goes from 0 to n minus 1, is greater than 0. Okay. So, this simply means that for every I and j belonging to 1 to the power n, which implies that there exists a directed walk every pair of nodes I and j. Which simply implies that G is strongly connected. Okay. Let us look at the reverse side of the proof, which is C to A, meaning now let us assume that G is strongly connected. Does it imply that A is irreducible? Let us see. Now, G is strongly connected implies that there exists directed walks between every pair of nodes. This simply implies that let us write it, there exists directed walks between every pair of nodes of some length L. This further implies that there exists walks. So, this further implies that there exists directed walks between every pair of nodes of, let me call it some Li or something, of length some L bar I, which is strictly n. So, how can we say that? We can say that because all that we need to do is the lengths of walks greater than n are as a consequence of the cycles in the network. So, we simply subtract all the closed sub walks from within this directed walk to obtain lengths which are smaller than n. Since we know that between every pair of nodes walks of lengths less than n definitely exist, this implies that summation of a to the power k from 0 to n minus 1 will definitely be greater than 0, which further implies that A is irreducible, which completes this part of the proof. Okay. Now, let us look at some more properties which are associated with it, which is C to D. Again, C was that G is strongly connected, or as C, which we have been writing before. This implies that for all the partitions that are there, let us write it, of the node set up to n, there exists a directed walk I comma j where I belongs to I and j belongs to capital J. Okay. Now, let us try to, so the proof can be done in a very straightforward manner using contradiction. So, we only need to assume that this property does not hold, and we can very easily show that the graph will not remain strongly connected anymore. So, since this is a very easy proof, I will leave it for the students to solve for themselves. Please try this out, and we will look at the reverse direction now, which means that we have the partitions such that in whichever way we partition the node set, there will always exist some edge from one node to the other, from one node set to the other node set. And then we show that if this property holds, then the graph itself becomes strongly connected. Let us see. So, we start by picking some node I from the overall node set. Okay. Now, let us denote R I as a set of all those nodes which are reachable by the node set I. Okay. Now, so we have now some set of nodes R I, which are simply all the nodes from where there exists, which are simply reachable by the node I, meaning we can construct directed walks from I starting to all those nodes in R I. Let us construct another set U I, which is nothing but this, meaning it simply has all those nodes which are not in R I. We assume that the digraph is not reachable. This would imply that the set U I is actually non-empty. So, what do we have? We actually now have two partitions of the node set R I and U I, meaning the node set 1 to n can be written as the union of R I and U I. What does statement D say? It says that whenever we have any two partitions of the node set, then there always must exist an edge from one partition to the other, meaning this would imply that there exists some A, say j h, which is greater than 0, where j belongs to R I and h belongs to U I. What does this imply again? This implies that there exists an edge from R I to h. In other words, there exists an edge from I to h, because remember we defined R I as a set of all those nodes which are reachable from I. Hence, what we have found is that there also exists an edge from I to h, meaning h now instead of belonging to U I must belong to R I. So, if we repeat this process iteratively, we will eventually get that the set U I is an empty set, which would imply that every set in the every node in the node set is actually reachable by the node I, meaning that the network is strongly connected. Is reachable by I. Since I is any general node, this holds for every I in the node set, which implies that the digraph G is strongly connected. Now, let us prove the part from B to D. Just to remind you, B says that there does not exist a permutation matrix P such that P transpose becomes block triangular, and again D talks about the existence of or the non-existence of partitions which do not have any edges from one partition to the other. Okay. So, let us start from B to D. To do that, we start by assuming let there exist a partition I comma j of the node set I to n such that A I j equals 0. where I belongs to capital I and small j belongs to the partition capital J. So, meaning that we are assuming that we have some partitions such that there does not exist an edge from one partition to the other. Okay. And we will gradually prove that this is not possible. So, in order to do that, let us start by defining a suitable permutation matrix. Now, let P be some permutation matrix which basically maps all the entries pertaining to the partition I as the last entries of the node set, meaning of the node set, where this denotes the cardinality of I. Okay. So, what does this imply? It implies that now when we write PAP transpose, we get something like this, or since we have it in the form of A itself, we can write this way, and AII. So, basically this is what a permutation matrix does. Remember that we started with the assumption that there does not exist any directed edges from the partition I to partition J, meaning this entry here becomes equal to 0, which implies that PAP transpose becomes block triangular. Which is a contradiction, because we started with the assumption B, which says that we should not be able to find a permutation matrix which can make the A matrix block triangular, but clearly we have done that, meaning we have arrived at a contradiction. Hence, there does not exist any partition such that we can have Aij equal to 0, which completes the proof from B to D. Can exist. Okay, we'll stop here. Now, the other part D to B can be proven in a similar manner. So, meaning we have now shown that all of these properties are actually equivalent to one another, meaning if we start with the matrix A being irreducible, then we know for sure that the graph associated with the adjacency matrix actually becomes strongly connected. And similarly, we know that there will never exist a permutation matrix P that can actually make PAP transpose block triangular, and there will also it will also not be possible to construct partitions of the node set I and J such that there do not exist any edges from one partition to the other. We will not be able to do that, meaning in whichever way we partition the node set, we will always end up having some edges from one node from one partition to the other partition. Okay. Okay, so these are some graph theoretical properties that are associated with the adjacency matrix A. Now, let us look at in some ways these properties can be used to talk about the global reachability of the adjacency matrix, or global reachability of certain nodes in the adjacency matrix. So, how do we do that? Okay, let's look at some examples to understand how the powers of A can be used to understand global reachability of a certain node. Okay. So, in this particular digraph, we see that the globally reachable node is node 2. Okay. And okay, let's start constructing the walks. Which are the walks of length 1? That is 1 to 2, and then 3 to 2 and 3 to 1, meaning these are the only entries which are greater than 0 and the rest of the entries will be equal to 0 in the matrix A. Let us write it 3 2 these. Okay. How many walks are there of length 2? We see that there is just one walk of length 2, which is 3 to 1 to 2, meaning only one entry here will be non-zero, which is equal to this, and the rest of the entries become equal to 0. So, now let us look at this summation k equals 0 to n minus 1, n minus 1 in this case is equal to 2, and the summation is of a raised to the power k. So, this is simply equal to I plus a squared, which gives us and a is this. Okay. So, this is the matrix that we get here. Notice that, notice that the column associated with node 2, which is a globally reachable node, is strictly greater than 0. So, is this a property that holds only for this particular digraph, or is this a general property which holds for every globally reachable node in every digraph? Let us look at another example. Okay. So, in this case every node is globally reachable as the digraph itself is strongly connected. So, the globally reachable nodes are 1, 2 and 3. So, what should we get? By our, based on our previous example, we should get a raised to the power k, k being equal to 0 to 2, k going from 0 to 2. This entire summation should be equal to 0 as all of the nodes are globally reachable. Okay. Let us construct the A matrix. So, let me directly write it 1 and 1 1 0, and A squared becomes equal to (0 1 1). So, if you work it out, it is going to look like this, and the summation then becomes what do we see here? We see that the column associated with node 1 is greater than 0, the column associated with node 2 is greater than 0, and the column associated with node 3 is also greater than 0, which is consistent with what we got in the previous example. Meaning, we can conclude that the jth column of e to the power k is positive for every globally reachable node. Globally reachable node. Okay. let us focus our attention on the matrix A square. We see here that A square has several entries which are equal to 0. Can we add an edge in the digraph in such a manner that the number of non-zero entries in A squared can actually be increased? So, I would ask the students to pause the video right here and try this out. Just add one edge in the network so that the non-zero entries increase and the zero entries reduce. Okay. I hope you have tried that by now. Let me give you an answer to that question by modifying the previous graph slightly, simply by adding a self loop. Okay. So, let us now do the construction. The globally reachable nodes remain the same 1, 2 and 3. Now, the A matrix becomes and A squared becomes zero and 1, 1, 1. So, let us focus our attention only on A square. What do we see here? Simply by adding just one self loop in the network in the digraph, what did we get? We actually reduce the number of zero entries to only 1. So, this is what self loops can do to a network. They improve the connectivity very nicely. So, the self loop has actually helped us make A square or A to the power k in that matter less sparse. Okay. Let us change this slightly by adding one more self loop here. What do we get in this case? Now, if we add one more self loop, our A square simply becomes, let us start by writing the A matrix. Zero, zero, 1, 1, 1 and 1, there is a self loop at 3, and A square now becomes equal to this. So, what did we observe here? We observed that we need not have to wait for the summation. So, of course, the summation here is greater than 0 in both of these cases. But not only that, in this case we directly get that A square becomes completely greater than 0. How is this possible? Sorry. This was possible because of the self loops that are present in the digraph, meaning self loops can actually lead to some nice properties associated with the adjacency matrix of a graph. We can conclude with the following results. Let us see. So, suppose we start with G being a weighted digraph with at least 2 nodes and a weighted adjacency matrix A. Then the following points are equivalent. First is the jth node is globally reachable. In that case, the jth column of summation, this summation of A raised to the power k, where k goes from 0 to n minus 1, is positive. So, we saw several examples of this already. Now, yet another interesting property holds, that is, now if there is a direct walk from node I to node j of some length k, and at least one of the nodes has a self loop. One of the nodes along the walk has a self loop. In that case, I to j is reachable via walks of lengths starting from k up to infinity. Let us quickly see an example of it through, let us quickly see an example. So, suppose we look at this diagraph, we see that the node 2 is globally reachable. And if we start creating walks from node 3 to node 2, we see that, this should be via node 1. We see that node 1 here has a self loop. So, this is a walk of length 2, but because of the self loop, we can now easily construct walks like this, meaning we keep going around the self loop. Since we can do that arbitrarily many times, so this is a walk of length 3, a walk of length 4. We can similarly create, by repeating this, by traversing around the self loop multiple times, we can create walks of arbitrary length which start from 3 and end at node 2. So, this is how self loops are useful. We can actually create walks of desired lengths using the self loops. Let us look at yet another result. Again, let us start with G being a weighted digraph with at least 2 nodes and a weighted adjacency matrix A. An additional property is that there now is a self loop at each node of the digraph. In that case, the following properties hold. The first one is that the graph G, let us say if it is strongly connected, then a raised to the power n minus 1 is strictly positive, which makes the matrix A a primitive matrix. Okay. Let us quickly look at an example of it, but before we do, let us look at a more relaxed version of this. Now, instead of the graph G, the digraph G being strongly connected, let us now relax by saying that one of the nodes is globally reachable, meaning the jth node is globally reachable. In that case, because of the presence of the self loops, now the jth column of a raised to the power 1 has positive entries. And here is an example of it. If we see that the digraph here has a self loop at each node, and when we compute a raised to the power n, we observe that the second column, which is associated with the globally reachable node 2, actually has all entries which are positive. So, now again all that we need to do is we simply need to look at the powers of the matrix A, and we can conclude more about the properties of the digraph, meaning whether or not there exists a globally reachable node and how many walks exist to that node. All of these properties simply can be constructed by looking at the adjacency matrix A and its powers. So, we will conclude with this. In tomorrow's lecture, we will look at some spectral properties that are associated with the matrix A. Thank you.